We spent a significant amount of time talking about the structure of atoms. However, in this next unit, we are going to spend some time looking at how atoms bond to other atoms. We're going to actually start with asking the question, why do atoms bond? Because most everything around us is not consist of elements in a pure state. Most everything around us consists of compounds, which are atoms that are bonded to one another in some way. So why is that more common for atoms to be bonded rather than exist in a pure and elemental state? Well, to answer that question, we're going to look at something called the second law of thermodynamics. Okay, you're going to want to remember this. This says that all systems will move to the lowest energy state possible. So what does that mean? So for an illustration, when you were a child, you probably stacked blocks. You figured that you could put one block on top of another block on top of that. And after a while, most kids try to build the tallest tower possible. Now, at some point in time, you realize that there's kind of a limit to how high your tower can be. When you get past a certain point, the tower starts to get really shaky no matter how carefully you stack the blocks on top of each other. The reason is that if you stack blocks on top of each other, the amount of energy that you're putting into your tower increases. So you get a high energy tower. And so the natural tendency of the universe is for things to be low energy. So after a while, the tower reaches a point of instability that can't be maintained any longer, and it falls, it collapses. And when it does, those blocks scatter everywhere, and that's your low energy state. Well, that's all well and good for blocks, but why does that apply to electrons? So the question is, what is low energy? What is a low energy state for an atom? Well, to answer that question, let's look at, we have a group of compounds that do not bond, and these are the noble gases. Since the noble gases don't bond with other atoms, most other things bond, there must be something about the noble gases must already be a low energy state. So something about the noble gases. Well, it can't be how many protons there are, because they all have different numbers of protons. And it's not the number of electrons either. However, it does have something to do with the electron configuration. Now, if you look at where the electrons are located, where the noble gases are located on the periodic table, they're this last column. Okay, and if you remember from doing your electron configuration, you remember that these are always at the end of the row, so they always have like a S2P6, so 2S2, 2P6, 3S2, 3P6. What's actually happening is that they have a completely filled up energy level. Okay, they're at the end of the row, so all of their orbitals are completely full. There's no half-filled orbitals, and they have both full S and full P. So they have the lowest energy electron configuration possible. That they have completely full energy levels. So having full energy levels appears to be the lowest possible energy state for an atom. So what this means is that other atoms, besides noble gases, are going to seek to alter they're going to alter their electrons to mimic the configuration of a noble gas. Okay, so what we're going to do in this first objective is we're going to talk about one way that atoms can do this. And this is called the ionic bond. So first of all, let's look at where ions come from and what is an ion. What's this ion thing? Okay, so let's look at metals have a few valence electrons. They have somewhere between 1 and 4. If you look at your periodic table, okay, you'll remember that this is the alkali metal family with 1 valence electron, the alkali earth metal family with 2 valence electrons. These here, remember we said that the number of valence electrons is variable, but in general it's around 2. All the metals in the boron family, which would be aluminum through here, have 3, and all the metals in the carbon family have about 4. Okay, now we have antimony and bismuth. They're kind of unusual metals, but they actually have 3 valence electrons, or it's a little weird. They don't follow the same pattern as the nitrogen, the rest of the members of the nitrogen family. But basically the point is that metals do not have a lot of valence electrons. Now, in order for valence electrons to mimic their electron configuration and have full energy levels, they're going to need to give electrons to another atom. To be stable. Stable, the term stable means low energy. So something that has a lot of high energy is usually an unstable system, okay, and a low energy is usually a more stable system. Okay, so when they give the electrons, what happens is that their energy levels usually have a few extra electrons in them, and when those are given away to a different element, okay, their energy levels, the outer energy level is actually emptied out, and the one underneath, if you will, okay, the next energy level down, is filled up. So that's why it looks like, has the same electron configuration as a noble gas. Now, special mental note, atoms that do this don't turn into noble gases. Otherwise, every time anything bonded, it would become a gas, and we know that doesn't happen. We have lots of solids and liquids. The point is, though, when they give away the electrons, is that then they have more protons than electrons now. Okay, this means that there is more positive charge than there is negative charge. So they become positively charged. Okay, the term for a charged atom is an ion. Okay, and positively charged ion is a special name, cation. Okay, so that's what the metals do. What about nonmetals? Nonmetals have a lot, have many valence electrons. Five to 7. Now I'm not including the noble gases, because the noble gases have 8. Okay, that's the maximum number of valence electrons you can have. Okay, they're going to take electrons from another atom. You can kind of see that metals and nonmetals can kind of help each other out. Okay. So nonmetals, when they take electrons, then their outer energy levels get filled up. So they kind of fill in the holes, the missing pieces, and then they have the same number of electrons in their outer energy level as a noble gas. So they have this opposite situation. Since they've taken additional electrons, they don't have the same number of protons, electrons anymore. They have more electrons now than protons. Okay, so more negative charge than positive charge. They're negatively charged, and a negatively charged ion is called an anion. Okay, so a cation is positively charged. It's a metal. And an anion is negatively charged, and they're nonmetals. Now, if you remember, positive charge is always attracted to negative charge. Okay, so a cation and an anion are formed when a metal gives its electrons, its valence electrons, to a nonmetal. You've had to get a positively charged cation, a metal cation, and a negatively charged nonmetal anion. They are then attracted to each other. Okay, the attraction between positive and negative charge has a special term. It's called electrostatic force. Okay, attraction between positive and negative charge. Electrostatic force is as strong a force as gravity. It's irresistible. And you may have played around as a kid with magnets, and you find that positive, there's a north and a south end of a magnet. Magnetism and electricity are interrelated forces. Okay, so the positive and negative ions are attracted to each other through electrostatic force. Okay, so that's what we call the ionic bond. The ionic bond is the force of attraction. It's the electrostatic force between a positively charged metal cation and a negatively charged nonmetal anion. Now, if you haven't got your periodic table out yet, go ahead and get your periodic table out, because then we're going to talk about something that's called oxidation number. Oxidation number is the charge on an ion. Okay, and it's based on the number of valence electrons given or taken. Okay, so positive cations are metals, and it's the number of valence electrons given. So for the negative anions, these are the nonmetals, and the number of valence electrons taken. That will be the oxidation number. Now the oxidation numbers, okay, have a pattern, and that is all families on the periodic table have the same oxidation number. There are a few exceptions that we'll talk about. Okay, why? Okay, because elements in a family have the same number of valence electrons. Okay, so the oxidation number is based on the number of valence electrons given or taken. Since elements in a family have the same number of valence electrons, they're all going to give the same number, or they're going to take the same number. All right, let's go to our periodic table. Okay, we're going to start with the alkali metal family. The alkali metal family has one valence electron, and since metals are givers, okay, they will give away one valence electron. So metals are always positive, so the oxidation number for the alkali metals is +1. Okay, that means that when alkali metals form ions, they give away one valence electron, and they have an oxidation number of +1. They have one extra unit of positive charge than normal. This is the alkali earth metals. They have two valence electrons. They're still metals, so when they give it away, they'll have an oxidation number of +2. Now, we're not going to put anything for the transition metals yet. We're going to come back to this in a couple of learning objectives and talk about them. Okay, we're going to skip over to the boron family. The boron family has 3 valence electrons. The majority of them are metals. Okay, boron acts pretty much as a non-metal, right? But the majority of them have metals that 3 valence electrons, so they have an oxidation number of +3. Okay, now we're going to jump over here and make our way backwards. Now, the noble gases over here, remember they have 8 valence electrons, but they do not bond. They do not form ions. Their oxidation number is 0. They're not going to form positive or negative ions. Now, let's look here at this family, the halogen family. The halogen family has 7 valence electrons. They are non-metals. So they are going to need to have the same number as the noble gases. They're going to want 8 to fill up their energy level, so they're going to need to take 1. So they're negative because they're non-metals, and they're going to take 1 valence electron. Their oxidation number is -1. Okay, so they form anions with a -1 charge. They have 1 extra electron. Okay, moving on to the oxygen family. The majority of the oxygen family members are nonmetals with 6 valence electrons. Nonmetals will take, and they need to take enough to be noble gases, so they're going to be taking 2. 6 plus 2 is 8. Okay, nitrogen family, 5 valence electrons. Okay, it's going to take 3. This 5 plus 3 makes 8. Now, the carbon family is kind of split almost evenly between metals and nonmetals. The metals have 4 valence electrons. The nonmetals also have 4 valence electrons. So this family actually splits the difference. The metals in the family will give away their valence electrons for a +4 charge. The nonmetals will take 4. So this family kind of has 2 oxidation numbers, if you will. Okay, so for example, calcium. If you want to know what's the oxidation number of calcium, all alkali earth metals have an oxidation number of +2. If you want to know the oxidation number of arsenic, Arsenic's oxidation number is -3, the same as all of the nonmetals in the nitrogen family. Okay, so in your worksheet, you're going to practice. Say, all you need to do is make sure that your periodic table is labeled with the oxidation numbers, because you're going to be looking this up a lot in the rest of the unit.